I'm honored to have the chance to introduce our work here. I will introduce our paper, Neural Machine Translation with Word Predictions. I will introduce our work in the following parts. Let's start with background. Firstly, there is some notations we denote the source sentence as X and the target sentence as Y. The hidden state of the encoder are H and hidden states of decoder are S. Several neural machine translation systems are based on encoder-decoder framework. So I will introduce the encoder-decoder framework to explain our motivation. The words of the source sentence are fed to the neural machine translation system based on the encoder-decoder framework. The encoder encodes source sentence through a bidirectional recurrent neural network, and then obtains the initial state by averaging all the hidden states in the source sentence. The decoder generates each target word at each time step. The process starts with the initial state obtained by the encoder. So intuitively, we think the initial state should contain all information from encoder because it's the first state for decoder, which decides the whole translation process. Similar to this, after the initial state, the hidden states of the decoder control the translation process. We think each hidden state should contain all untranslated information, because each hidden state could be seen as the initial state for the rest of the target sentence. In summary, we think initial state has all target information, and the hidden states of decoder have target information which haven't been translated. And the transition of the states represents the transition of the information, which in turn affects the translation quality. So the initial state and the hidden states of decoder play an important role in the translation. Now it's the motivation part. We take a look at how these states are controlled. The red arrows in the figure show the arrows bug propagate through the network. The parameters will be updated when a word is wrongly translated. For example, if the YJ is a translation mistake, the error will transmit from YJ to the encoder. It takes several time steps for the initial state and hidden state to update their parameters. This supervision is weak and may be noisy. Combining the background, we make a summary of our motivation. The initial state and hidden state play an important role in the translation, but they are not well controlled in the current framework. Propagating translation errors through the end-to-end recurrent structures is not enough to control the hidden states and the initial states. This part is our approach for this problem. We use word prediction as the basic mechanism. The aim of word prediction is to predict all target words will be generated as the translation, different from generating the translation, which is generate an ordered word sequence. The prediction task only predicts the set of words which ignores the order, as shown in the figure. The translation task needs to translate the sequence follow the order Y1 to YJ. But the prediction task only needed to ensure these words, for example, Y1, Y2, could be predicted. We think the initial state contains all target information. This means it should contain all words information in the target sentence. And then, for any state in the decoder, since it will be used to translate the remaining sentence, it must be capable of predicting the words in the remaining sentence. So we can use the word prediction as an additional supervised. Word prediction is very similar to the translation mechanism in the output layer, which is very easy to implement. What's more, since all the words are already provided in the reference, no additional data or label is required. We propose two methods to add the word prediction in the initial state and the hidden states of decoder respectively. We denote them as WPE and WPD. First, I will introduce the WPE model. We think initial states contain all information about the target sentence, so it should predict all words in the target sentence. So we added a task for the initial state that it needed to predict all words in the target sentence. The formula is as follows. We map the initial state to the vocabulary size of nonlinear transformations and maximize the probability of all words in the target sentence. Please note that the maximization provides a direction supervision to initial state. For example, the parameters that generate the initial state. Using almost the same way, we need the prediction in all hidden states of decoder. For the decoder hidden states, there is no reason to prediction all the words, especially those which haven't been translated. So the target of prediction is those words which haven't been translated. The formula is as follows. We map all hidden states to vocabulary and max the probabilities of words which haven't been translated. The two methods are used in the training stage and enhance the representation of the initial state and the hidden state respectively. The testing stage is exactly the same with the original model, so it will not add the cost of decoding. Besides using the word prediction to improve the training performance, we also think about the other benefit of the predictors. Because large size vocabulary is one factor of slowing down the testing efficiency of NMT system. A natural thought is that the predictor could be used to reduce the size of the vocabulary. If we can extract a small exact vocabulary for each source sentence, the efficiency of decoding will be improved. So in the testing stage, we could use our word predictor to generate a small and exact vocabulary and use the new vocabulary to translation. If the prediction is accurate, the translation quality will not be affected. The specific procedure as follows. After the encoding stage, we use the initial state and the word prediction to predict top keywords and use the top keywords as the new vocabulary to decoding. In the experiments part, we will demonstrate the word predictor's performance is high enough to extract an exact vocabulary. I will make a summary of our proposed method. In the training stage, we could use the word prediction mechanism to enhance the representation of initial state and hidden states. And during the testing stage, we could use the word prediction as a word predictor to improve the decoding efficiency by reducing the vocabulary size. I don't show the detail of the implementer. More information can see our paper. Here are the experiments. We perform experiments on the Chinese to English and the German to English machine translation tasks. We use the NIST corpus in Chinese to English experiments, and it includes about 8 million sentence pairs as training set. We use the MT02 as a validation set and MT032, MT04 as test sets, and each sentence in the test set has 4 references. In the German to English experiments, we use WMT14 corpus in German to English experiments. Use the news test 2012 as validation set and the 2030 as test set. Each sentence in the test set has 1 reference. For experiment setting, we follow the default setting of DL4MT. The source and targeted vocabulary are limited to the most frequent 30,000 words. The auto vocabulary words mapped to a special token UNK. using EOS as the end of sentence symbol, and use byte pair encoding for German to English corpus. This result are case insensitive 4-gram blue scores of our model and baseline. Our model improves 4.5 blue compared from the baseline in the Chinese to English experiments and improves 1.3 blue in the German to English experiments. Because we use the prediction to improve the training performance, it will add the time of training stage. We also perform experiments to compare our method with other training techniques, such as dropout and ensemble. Our model obtains the highest score compared with the base model with dropout or ensemble techniques. Our model, together with the ensemble, can improve the 5.79 blue score and 1.79 blue score compared with the baseline model in Chinese to English and German to English, which shows that our method enjoys extra benefits besides the ensemble. These experiments show the performance of our predictor. The PREC is a shortcut for precision. It's easy to see that in both position and recall, our model is higher than baseline model. For the range between 1,000 and 10,000, the recall of our model is high enough. When the prediction size is top 10,000, the recall can attain 97%. It shows that our model can extract an exact vocabulary, which size is smaller than 10,000. This experiment shows the efficiency improvement from the word predictor. The chart on the left is the change of translation quality with the changes of vocabulary size, and the chart on the right is the change of decoding time with the change of vocabulary size. The dotted line is translation quality and the decoding time in the fixed vocabulary. In the red rectangles, we can see that when the size of predicted vocabulary is between 5,000 and 7,000, the translation quality is close to the best performance, with about only 16% of the time. Now I present some translation cases from the test set. I don't know. The baseline model translates the internet M of Time Warner into the internet company said on the internet the red underline and those two parts are correctly translated for our modes. The internet company of Time Warner and advertising and commerce. Here is the conclusion. The bug propagating provides no direction control of the information carried by the initial state and hidden state. What prediction uses a natural annotation which brings direct supervision. It sought to enhance both the initial state and the hidden states of the decoder. Additionally, with the word prediction mechanism, smaller vocabulary size can be produced during the decoding, which improves the decoding efficiency. Thank you for your attention. That's all.
Thanks for the talk. So if I understand correctly, your baseline NMT model did not include an attention mechanism.
With attention, I don't show it in the figure. With attention.
Ah, you do. Okay.
Yeah.
So you're trying to you're forcing the model to contain more information about the future.
Can you speak loudly?
Yeah. Can you hear me now?
Yeah.
So you're forcing the model to encode more information about the future. But have you tried also enforcing it about remembering the past? In the decoding, for example, you could also insist that every state knows which words were already generated. So in the decoding stage, while training, you're forcing the model to know which words are going to follow till the end of the sentence.
Yeah.
But you could also say that every stage, the model should know not only which words are going to follow, but which words preceded it.
Oh,
So you could try to generate to know about the bag of words for the entire sentence as well. I don't know how much that would change things.
huh?
So you could do that, and I don't know how much it would change.
Yeah, thank you. I don't think that. I will try this.
Thank you. This is very interesting. I have a small question. Why don't you use BPE for Chinese, source-side Chinese as well? You said you used BPE for bi-pair encoding for German to English, but not for Chinese to English.
In fact, if I don't use the BPE for the German to English, the baseline is too low.
But using BPE on Chinese also improved, I mean, at least in my experience, also improved BLEU score and also reduced the vocabulary size down to like 10K. It's good enough. And then your kind of word prediction won't have that much of an improvement because, you know, it's already 10K after BPE.
I don't try it, but I think if I use the BP in the Chinese to English, the baseline will improve, and our method can also work because it can work in the German to English, but sometimes it may don't can improve so high.
Okay, let's thank the speaker one more time.
Thank you.